I think so all of these
yeah, typically the problem with the longest here is like the file is too big or it takes too long and it's trying to do it, you hit a deadline. CD there. So you might just like upload it to like say GCS, like to the cloud storage or the blob store app entries, and then instead of the data store, and then be able to like just leave it out of there and process it. So that's another way to do it. Because like if it's in GCS, it's just you just take the file itself and save it there, and then process the file later. It's part of the task too. Can you use the task too at all?
Thank you.
It can do pretty well.
有这么困难吗？
你有在直播啊？这样
你直播不是挡到了？
没有，我要先贴连结。
If I were you, this is what I would use probably. Depending on the size of the CSV file and what exactly you needed to do. But usually, what you want to do is like for stuff like for large amounts of processing, like process many records and CSV or something like that. It's like you run it and it has to use the background. So,
还是我没放，
是吧？
非常非常。
Yeah, so you can from the task you can update that.
去找那个啊，下次去接那个接录影的材料一样，对啊，没有约你，我知道你一定不合作不约。
So yeah, you can update my text from the task too, but that's not a problem.
好，你的中间下把它走，这样可以吧
So then basically what you do is you create a task
？Simon，
you like write a file for the
帮我擦一下。
cloud storage, and then you would pass the path to the task file to the task, and then the task would take that file and read it from the blob store or from GCS, and they would process the file.
你就是等你什么都要放的。
And then at the end, you kind of
帮 GCP 的 member 强力招募一下。
you do have to be like careful about like how you handle whatever because it'll be it runs in the background, so it runs parallel to like two requests that are coming to your server. So if you're updating a bunch of different keys and then
就像用你的电脑。
啊，他们要走了啊？
哎，放这边我压力很大，你知道？
为什么？
我碰好像会碰掉。
哪里
？OK，我们现在开始下一场的节奏，下一场的 session。那在这个之前呢，因为有一个 gcpug 的 member 要我帮他广告一下。那Q member 现在在征暑期的工读生，那欢迎这种就是家里面已经有小朋友，3岁就可以接受，不接受对不对？好，那原则上如果有小朋友想要就是接触technology， 因为原则上他们技术非常的强。那如果有这一类的兴趣或者想法的话 ，OK， 欢迎跟Joyce，OK， 跟 Joyce 联络 ，OK。那希望接下来我们就欢迎我们的data flow 的工程师来跟我们介绍一下有关于 data flow、data graph 这些新的技术，这些都是蛮特别的 technical 的东西。那我们把摄影机交给摄影机，把荧幕交给 交给 Abra， 因为他名字我看了好多次，我都不知道怎么念。OK，Abra， 我们欢迎 Abra 老师。
Hey guys, can you hear me okay? At the back? Yeah. Alright, so I'm going to talk about big data at Google. I'm also going to give a little overview of data flow and data proc. The format of this session is going to be some talk followed by some deep dive on data flow. What does it take to write data flow code? And I'll show you a quick demo of data proc. If there are any questions, please raise your hand or just shout it out, keep it interactive. I don't want to make it very formal, so just keep shouting if there are any questions. So here's who I am. I am the engineering director for data flow and data proc, and internally, excuse me, also manage Millview, Flume, and MapReduce. How many of you know MapReduce, Flume, or Millview? Show of hands. MapReduce? Most of you? Flume? Anybody? Evolution of cloud is very important in the context of GCP. If you go back to late 90s, early 2000s, there was a movement to have what we now know as colos, co-location facilities. That was the first evolution of getting a cloud offering started. What that means is there were companies that provided you space to host your servers. There were companies that provided you power, all the facilities within that colo. But you were responsible to bring in your servers. You were responsible to actually cable it up. You were responsible to make sure that entire setup actually worked. Since then, we've come a long way. And what you see here is typical cloud 2.0. So if you go to today's cloud offering outside of GCP, what you're going to get is not just the space and power, but you also get pre-configured boxes. If you get a bunch of VMs from a cloud provider of your choice, what you're going to get is a few Linux boxes and some things that's already cabled up. However, if you want to put any customized software on it, you're still responsible to configure that software. You still have to put your databases on it. You still have to put your storage on it. You have to connect all of these systems together to make sense out of it. This is a very typical scenario on Cloud 2.0. However, at Google, all of our developers do not do any of this stuff. They are responsible to write code. They do not get involved with configuration. They do not get involved with pushing the code out. They do not actually get involved in scaling the system, managing the system. You write your code, you upload it, somebody else takes care of for it for you. How is that possible? So we do a bunch of automation, and that is what has given rise to Cloud 3.0. So what you see as a part of Google is really GCP or Google Cloud Platform is really what we call 3.0, where you write your code and you let the system underneath take care of how do you provision, how do you deploy code on it, how do you scale, how do you manage all of that for you. It's an important piece of information because you're going to see a consistent theme for all of the product offering that we have that's going to follow this pattern. Any questions so far? So far, so good? Yeah? A couple of people nodding? All right. Sounds good. Okay, so typical big data scenario in Cloud 2.0, in this sort of an arena, what do you end up doing when you have very complex data? Excuse me. You spend time programming, which is very common. You have to write your business logic. You also spend time provisioning your resources. You also spend time in handling the growth. If you have a spike in your traffic, you are responsible to procure more capacity, make sure that the system actually stays up. When the spike dies down, you want to take away the capacity, otherwise you're going to have wasted utilization. You also want to monitor your utilization in steady state so that you're not spending more money than you have to. You have to worry about deployment, you have to worry about configuration, you have to worry about reliability so that if the system does go down, you have failover protection in your system. So what we want to do with Cloud 3.0 and GCP specifically is take away all of that weight. We want you to focus on programming, and we want you to really spend time digging through your data. At the end of the day, identifying more value from your data is only possible if you have more time to dig through it. Those of you who use data on a daily basis, terabytes of data, it's not easy to find insights from it. There is just too much of that data available. So this is really what we want you to remember. Okay, so let me skip over some of these things. Let's talk about what does it mean to have big data portfolio of activity. So what is the first thing that you want to do as a part of any big data deployment? You want to capture. Outside of collecting the data, there's not much you can do. If you don't have data, there is no big data. So you want to capture it. Once you capture the data, you probably want to store it. Either during storage or after you store it, you probably want to process the information, process the data. You want to analyze some parts of it. You may even want to visualize it. And oftentimes what happens is the information that you extract from your data is something that you're going to feed back right into your storage system or your analysis system. So take an example. Let's say you identify anybody who work in the gaming industry here, anybody games developer, anybody who's, which is the biggest group of developers, what industry do they come from? I can take a specific example. Any idea? Retail, online, media, all mixed? All mixed? Okay, let's take an example that's somewhat easier to understand. Right? Let's perhaps take a game example. Any of you play games? Forget who plays video games? Games. You obviously do. You develop them too. Anybody else? Nobody plays games? Really? Okay. Who shops? Online shopping? Anybody? All right. Thank you. So let's take an online shopping example. Easy enough. Assume as a store you're shopping online, and the store identifies you as a power shopper, somebody who shops very frequently. I don't know what the Amazon equivalent here is, maybe Taobao, these shopping sites, but you go there very often, and the store actually wants to reward you That information is possible once you process, analyze, and push that information back as you enter the store or as you're shopping. So this is the power of that data, data analytics that you can actually extract out. So what are the technology set that are available to do this within the GCP portfolio? That's important to understand. Most of you are probably familiar or have heard of Cloud 2.0. So data capture, Kafka. Some of you, most of you, at least a few of you hopefully know about Kafka. For storage, there is lots of databases: Cassandra, MongoDB, CouchDB, MariaDB, probably tons of them. HBase if you're in the Hadoop space. If you are in the Hadoop ecosystem to process and analyze, they're going to use Hadoop, Spark, Storm, Hive to run your queries, and so on and so forth. And to visualize it, Tableau, QLake, I think there was an announcement on QLake, either getting bought or buying somebody just now for like 3 billion. Pretty big thing. Anyway, equivalent technology set in GCP world is for Kafka, you normally end up using Cloud PubSub. It's the same set of technology, and I'll give you a few slides on it so you at least can grasp what PubSub is about. But imagine PubSub, publishing and subscribing, very similar to Kafka concept. For storage, we actually have very different type of storages. So you are able to store raw logs into cloud storage, GCS, as we call it. You can store structured data. So oftentimes what you do is you get raw data, you analyze it, you make some structure out of it, and you put it as known schema into BQ or BigQuery. So you have the ability to store structured information in BQ. If you are into HBase, really large databases, horizontally scaling databases, but no SQL, you can use Cloud BigQuery. That's possible. You can also use data store. Some of you who want to do a lot of transactional type of processing, a lot of reading, a lot of writing, a lot of reading, a lot of writing, for a sizable database, you can use data store, or you can use SQL or Cloud SQL. So many offerings depending on your choice. You have an option to pick and choose the type of storage. In terms of processing and analyzing, there are 2 or 3 things which are very important. There is Cloud Data Flow. I'll give you a brief idea of what Cloud Data Flow is. Yelena will actually give you what it takes to write a Cloud Data Flow. I'll talk about Cloud Data Prop, which is your managed Hadoop or Spark instances. And then we'll talk about BigQuery in terms of what it takes to analyze information. Machine learning, those of you who are into processing data will know that you can do a lot of clever algorithms on analyzing the information, creating your models, identifying scores, ranking the information as it goes through. All of that's possible through cloud machine learning. And then we have an offering called Cloud Data Lab for visualization. Okay. All right. Here is a very typical reference architecture that we see as a part of GCP. So there are 2 types of load for data processing. There is something we call batch load. If you know the data up front and you want to process this information, you have an option to do it using different bits and pieces of GCP architecture. And if the information is more streaming, you also have the ability to do it. So let's walk through this a little bit. When the batch information comes in, these are raw logs, right, typically, that you're going to get from your maybe web servers or maybe your phones or some other sources of information. You're probably likely going to store this into GCS, raw logs. Once the information is in GCS, you probably are going to read this through data flow to get and extract some value from these logs. And once you've extracted the value, you're going to put this into BigQuery so that all of these downstream people, your co-workers, your IT department, your finance, your legal analyst, can actually hit BigQuery and get some value out of it. If you are using streaming information as real time, as the information comes in, you want to analyze it, our Cloud PubSub will allow you to pull the information or read the information, or you can push it to it. It's the same information processing pipeline. You process it through data flow. You can put it into BigQuery. You can put it into Bigtable. You can put it anywhere you are. Any of these, if you go back, any of these storage systems are pretty much connected through data flow. So you can pick and choose the right storage system of your choice based on your use case, and you can make sense out of it. And Dataproc allows you very similar thing. If you have an on-prem Hadoop Spark Storm deployment, you can do very similar thing to get that deployment managed by GCP, but at the same time, read and write information into any of these BigQuery or cloud storage or anything of that nature. Any questions on this? If you were to map this into open source technology, your cloud pub sub would be Kafka for most parts. Your GCS would be HDFS or HBase. That's just a normal scenario. Cloud data flow is Spark, Storm, Kinesis, homegrown processing system. Your BigQuery typically would be Cassandra or Couch or Mongo or anything of that nature. And all of these other systems that you have are pretty much whatever storage systems that you pick. However, in your homegrown system, you will have to do what I call reconciliation. Your batch results are going to be the source of truth. Your streaming results are going to be quick and dirty. Oftentimes, when you do Lambda processing, Lambda architecture, you have to reconcile what you store in your batch information with what you get in your real-time information. And that's a very expensive process. With GCP, and specifically with Dataflow, you do not need to do Lambda processing or Lambda architecture. That's a huge advantage. If you're dealing with a lot of data, if you have both batch and streaming, the fact that you do not need to do Lambda architecture is actually a tremendous amount of saving. Any questions on this?
For our benefit, what is Lambda architecture?
So Lambda architecture is what most people end up doing, where if you have a batch or streaming information, you first store it into a permanent store, because that information is going to be your source of truth. However, as the information goes and flows through your system in real time, you want to extract some value out of it right away. The information that you get right away may not be as accurate as what you get with the entire data. Imagine you are a gaming person, or imagine you are even an online shopper or anything of that nature. It's entirely possible that you will have information which is a little bit late. You may not have necessary mobile connectivity. So you're going to store a bunch of information on your phone or on your whichever mechanism you use to browse. And when the information is available, you're going to do a mass blast. So all of that information in batch scenario, you won't have it available. However, in streaming, that will be late data. So you need to do this reconciliation from streaming to batch, and that's what people set up, two separate pipelines. And that's typically called Lambda. Any other questions? All right. So let me do a little bit of deep dive into what data flow, followed by what data proc, and what BigQuery is. I'll hand it over to Yelena. She'll walk you through a little bit more of how to write data flow programs. I'll come back, I'll do a quick demo of data proc, and then I think we'll do that. All right. So Apache Beam and Cloud Dataflow. I think there are two concepts here which are important. Beam is an open source part of the SDK from Dataflow. So let's dive into a little bit more of the detail. Skip over this, since most of you haven't played with Flume Java, maybe this slide doesn't make a lot of sense. But Beam is a let me go back here. So let's take a look at this slide. I'll go back to the example. But either you're batch processing or stream processing, you can have a beam model that satisfies both of this information that goes in. It gets compiled into a common model. You can run this model on an execution engine of your choice. You can run the beam model on Spark. If you have an existing Spark cluster, you can actually run it on Spark. If you have an existing Flink deployment, you can run it on Flink. You can run it on a local machine. And you can run it as a part of Google Cloud Data Flow. If you run the beam model on top of GCP, you're going to get Google Cloud Data Flow. So what we are doing is we are separating the SDK, the upfront APIs that you write your job in. That part is open source. Your execution engine, your choice. You can run on GCP, you get a very tight, nicely integrated experience. You run it on Spark, you can run it on Flink. So if you're looking to be as neutral or not get tied into a specific vendor like Amazon or Google or Azure, you can actually deploy this model and make sense out of it. Okay. And let me go back and quickly give you a simple example. I know it's a little bit hard to read, but don't worry about it. If you're interested, through Jelena, you'll actually see a lot of details on how to write this. But as a part of Beam and Spark, what you're going to see is anybody here use Spark? I just need to understand so I can either spend more time or want to. Okay. So I think for you guys, this will make sense. But if you're doing very simple batch processing, you have your data up front and you want to process that data, then the code for Beam and Spark is going to look very similar. You read the data, you analyze it, or you map it, reduce it, you're done. Simple. If you want to do it on a per window basis, which means I just want to evaluate this for 2 hours, 1 hour, 5-minute chunk of data, code is going to look very, very similar. Fun begins when you have big data. Remember I said, if you're playing games, you can run out of network connectivity, which means you will actually have a lot of data on your device. And when the network becomes available, you're actually going to blast that information. So the information happened way earlier in time versus when the server actually receives it. So if you have processed, let's say you started playing games at 4:15 p.m. today, and assume there is no network coverage. You go home and you get your network. And let's say it's 5 p.m. when you reach home. The event that happened at 4:15 will be received by the backend only at 5 p.m. However, somebody else who's using the games at 4:15, the server will receive the event at 4:20. So now if I want to know everything that happened at 4:15 p.m., either I'll have to wait till 5 p.m. till you reach home and your events are available, or I'm going to miss your events. Does it make sense so far? It's an important concept to understand. So to handle that sort of a scenario with Beam is very, very easy. It's built into the model. However, for Spark, it's not, and you have to do a lot of coding to be able to enable this data. It gets even more complex when you want to do sessionized information. For a given set of users, I want to do some specific actions. The information is again built into the Beam model. Versus for Spark or any other system, first of all, it's not even available, but if you try to build it, it's a very, very complex piece of machine. Okay. Right. So what you get with Spark typically is unified batch and streaming engine. But what you get with Beam is unified batch and streaming engine for sure, but also the same model and also the same API. This is a big, big, big difference. This is what makes Beam that much more powerful and that much more portable. Any questions so far? Okay. So we talked about this. Just to go over it again, this is what allows you not to do Lambda processing because it's the same data flow code that handles both streaming and batch. You don't need separate pipelines. You don't need separate bits of code. You don't need separate APIs. You don't need a separate model. Same set of model that satisfy both. And you can pick and choose your runtime as you deem fit. Okay. So what do we mean by it's a fully managed service? If I go back to my previous Cloud 3.0 slide, remember I said if you go back to this slide, data flow is a part of Cloud 3.0, which means it's fully managed for you. So let's understand what fully managed means. So it's auto-configured. You write your data flow code, you upload it on GCP, and it will take care of everything underneath for you. Provisioning the VMs, putting the right image on it, and deploying all the necessary dependencies and running your code. You do not have to do any of these steps, unlike any other cloud offering that you have. It's also optimized. So those of you who've written any code in assembly or C or higher level language versus lower level language will actually appreciate when you write, for example, assembly code, you're responsible for every instruction that you have to do. Move this information into this register, push the register, pop the register, so on and so forth. Versus writing it in C, that just says A plus B equals C, or C equal to A plus B. So what you're going to get is an ability to optimize and fuse some of these steps as a part of data flow, which makes it go that much faster versus having to do all of these steps manually for you. Autoscaling is a very, very critical part. As I mentioned, your specific graph of your traffic pattern will have very spiky behavior, very common, right? If you launch a new product, a lot of people use it, you'll see a tremendous spike in the traffic. And when the novelty dies, your traffic will go back. And suddenly you have a new year, and suddenly traffic will go up. People will do a lot of shopping. People might have a lot of free time. They might play a lot of games. People might be online, watch movies, whatever it is that your company supports. So it's entirely possible. We've seen traffic spikes from 500 requests per second, jumping to 50,000 and then dropping to 5,000 and going back to 500. If you have to scale the system on your own, how do you do it? Either you provision for the peak capacity, which is 5,000, 50,000, and then when the traffic drops to 500, you have so much free capacity that you cannot use. Wasted. So what we do as a part of data flow is we'll provide you on a scale. We'll detect that the information is being processed slow or there's an increase in the amount of data we're receiving, and we'll allocate appropriate number of boxes. And when we see the traffic go down, we'll actually deallocate them for you. So you are going to pay for what you need to use or what you are using versus pre-procured capacity. It's a big saving. Same thing with dynamic workload balancing. If there are jobs that are taking much longer than any other job in the system, we have the ability to redistribute that one job that's taking longer to everything else that's finished. So instead of your job taking 100 minutes, for example, when you redistribute it, it can take much lower. In this example, which is a real example, job went from 100 minutes to 60 minutes. It's a big improvement, as you can imagine. So we have the ability to do that. And then it's completely fault tolerant. So you don't have to write additional piece of code. If one of the stages in your data flow fails, we'll actually restart it, we'll reprocure new VMs, we'll transfer the state over, and everything gets started as if completely transparent to you. All right, any questions on data flow? We will do a deep dive on how to write data flow jobs in about 15 minutes, 10 minutes maybe. Any questions on this? All right. Let me give you a quick overview of DataProc, and then VQ, and then I'll tell you. So DataProc is a managed Hadoop and Spark deployment. Anybody here using Hadoop or Spark? Of course. Anybody else? Nobody? No Hadoop, no Spark user, really? I thought this is a cloud user group. Okay, No problem. If you're using managed Hadoop or managed Spark, if you're using Hadoop or Spark, one of the big problems that people have is managing your cluster at scale. Anytime you grow your cluster from a few nodes to tens of nodes or hundreds of nodes, you're going to run into a lot of the problem resides in keeping the cluster up versus actually running your jobs on the cluster. So we actually can take that pain away from you. We can start a big cluster that runs either Hadoop or Spark jobs in literally seconds. A couple of minutes, you'll have a pretty large cluster ready. These are preemptible VMs, which means if you do not need an SLA critical job, you can actually give your VMs to somebody else, and you will get a big discount on the amount of money you spend. It says 30%, but in some cases you can actually get 70% discount on what your spend is. It's a pretty big savings. Per minute billing. If you go to any other cloud, it's per hour billing. So if your job finishes in 61 minutes, you're going to pay for 2 hours. In this case, if your job finishes in 61 minutes, you're going to pay for 61 minutes. Imagine if you're running a lot of jobs that finish in 61, 62 minutes, you're going to end up spending 2 hours for each one of this versus just the time that you spend. And that's a big, big, big saving. Same topic, if your job takes 15 minutes, you're going to spend an hour versus 15 minutes here. So you've got to realize that. We also give you the ability to spin up clusters and destroy them as you need it. Which means if you're not using your cluster, you don't need to keep the capacity going. You can actually take the capacity away and then redeploy it as and when you need it. Again, big savings rather than having your capacity sit idle. You don't want that. And it's pretty fast. So ephemeral clusters is the ability to bring up the cluster. Short-lived is what ephemeral means. So you have the ability to bring it up and kill it as and when you need it. Very typical Hadoop deployment will look like this. Where you first deploy your cluster, you submit your jobs, then you start carving the cluster. This amount of capacity is for this job, the other amount of capacity is for this job, and so on and so forth. And what you end up doing is you manage the resources, you manage prioritization, you manage separation, because you don't want one job sharing other job's data and vice versa. You manage SLAs, all of the operations, pretty wasteful. What we do here is you need a cluster, you use Dataproc. For each one of these jobs, you can have a separate cluster that just comes up, job finishes, cluster dies. So you basically don't have to worry about resource segregation. You don't have to worry about separating the resources. You use it when you need it, and the cluster goes away. So imagine you're running different type of workloads. There are IT folks who need nightly reports. There are marketing folks that might say, I need reports every minute, ad hoc, I don't know, when somebody calls me, I have to put a report. And then there are other reports that you might generate, or other analysis that you need to do. So for each one of this, you can have a separate type of mechanism. Some might be a permanent cluster, some might be smaller, short-lived clusters. So we have this ability to do that. Your data remains in underlying GCS bucket. Your compute can come up and go down as a need. All right, I'll talk about BigQuery and then I'll stop and then hand it over to you. So BigQuery stats, these are actually pretty interesting numbers, and these are mind-boggling numbers. So the largest query by rows on BigQuery is 10.5 trillion rows. So trillion, these are not billion, these are not million, these are trillion rows. Right? So it's a very large number. Largest query by data size, 2.1 petabytes. Largest customer, that is in terms of storage capacity on BigQuery right now, 62 petabytes. Huge numbers. This is one customer. These are not multiple customers. Streaming ingestion at peak, we can take in 4.5 million rows per second. These are numbers that you're not going to see anywhere else in the system. Let's skip over this in the interest of time. So again, it's a completely managed service for you. You do not have to procure capacity. You do not have to manage anything underneath. We manage all of the growth. We manage all the deployment, all the upgrade. It's petabyte scale. It's really fast. You can write SQL, so you don't have to learn a new language. You don't have to do anything. Write SQL, you get your information out. It's basically based on Dremel, which is an internal tool to Google. And that Dremel code is actually working at Google scale. And any of you who know Google scale, it's unprecedented in the industry. It's probably the most unique in terms of data volumes, in terms of SLA, in terms of everything else that we do. So this BigQuery is actually validated at Google scale. So, and everything else, it's secure, durable, highly available, everything else that you should expect from a cloud product is all available. Let's go with that. One last bit of information, and then I'll hand it over, is, and this is very, very hard to do. I mentioned about auto-scaling. Let me give you an example of what that means. Assume this blue line is the capacity you have provisioned. However, this red line is what your workload actually needs. Because you have peaks, there are a lot of people who need to access the information at this time. There are few people who need to access information at low times. Which means at times like this, you're going to have idle capacity, wasted money. Times like that, you're going to have throttled information. Sometimes if you're running websites or even your games, you can see it very, very slow because the responses are not coming back fast enough, or websites are timing out because they just can't serve the traffic. So oftentimes what people end up doing is you will actually procure capacity for the peak load. Great, you can actually sustain this, but then what happens when you are in this part of the world? You have even more wasted capacity, correct? So what BigQuery will provide is it actually gives you capacity as you need it. So you don't have to procure more, you don't have to procure less. If your query needs to scale, it will scale. If the query doesn't need to scale, it will shrink. A lot of our customers are using BigQuery at scale, at petabyte scale, which is very, very large amount of capacity. And they don't even need to check with us. They just run with it. So it's a very, very simple, convenient to use tool. If you have any questions on that, feel free to come and chat with us. That's pretty much it. I won't go into Cloud PubSub since most of you are, it's like I can see a lot of hands go up on Kafka. So, I'll hand it over to Yelena. I'll come back. I'll do a hands-on demo of data prop so you'll actually get a feel for what this feels like. And Yelena will walk you through what it takes to write a data flow job. Yelena, all yours.
Hello everyone. So you heard a little bit about the data flow and Beam, Apache Beam. So I'm going to walk through a simple pipeline that we may want to build and to bring idea about the concepts we have in the programming model. Please interrupt if something doesn't make sense or it's not clear.
任何问题都会送一件 T-shirt. Any question and bracket can send a T-shirt. Okay, please raise your hand. Ask.
No, I mean it's usually I used it. We have any one? Oh. I think that's pretty sure it was this one.
You want to use mine? Yeah.
Direct?
Oh. You want to grab first?
Yeah, just okay. Okay, so the refresher on the stack. We have Apache Beam on Cloud Dataflow on Google Cloud Platform, okay? So, okay, now it's gonna work. Okay, so let's look at the Beam and data flow. You've seen the slide. So Apache Beam model allows us to do batch and streaming processing. And when you want to run your pipelines, you have currently 4 options. One is to run in open source world with Apache Flink and Apache Spark. And then we have direct pipeline runner for testing and Google Cloud Dataflow that you've heard quite a bit about from Apurva. So where did the Beam come from? The Beam came from pretty much 3 internal projects that were developed in MapReduce, in Google. First one is the MapReduce, which is one of the seminal papers that we published in 2004 that created a big data industry, pretty much. So what MapReduce allowed user engineers to do is to take the big data set, chunk it up into small pieces, apply a map function on each of these pieces, provide the key, produce the key and a value as an output of the piece, which are these guys. And then groups by key, so you get all triangles together, all circles together, or diamonds together. And then you apply a reduce operation on this group data and produce the final result. This was very powerful. It enabled people to go through lots of logs easily. And lots of people in Google used it. And in open source world, we got a Hadoop, which implemented this model, and now it's available to the rest of the world. If you're doing any serious data processing, a single MapReduce job won't do it. You need a sequence of MapReduces that will process the data. And to do that, like it turns out that the sequences can be really long, like hundreds of MapReduces. And it's very hard to follow what happens with your pipeline. So in Google, we came up with Flume Java, which allowed you to express what you're trying to do in terms of this data processing pipeline. And then the system would take this pipeline and convert it into MapReduces, because MapReduce was very optimized, scalable, and everything else. So this allowed Google engineers to focus on their application and not on how to run the MapReduce. At the same time, another thing that we discovered in Google was that we really cared about the real-time data. If you want to track the spam, like identify security risks and things like that, those are all real-time problems. So we came up with a mill wheel, which allowed us, again, to express the computations in terms of this, the computation graph, and this was a system that runs all the time, and it's processing data as it comes along. And this was very, very useful for a number of use cases, spam detection being one of them. And it's widely used in Google. So coming from these 3 projects, MapReduce, Flume Java, and Millwheel, we came up with the Beam model that you heard about from Apurva. And this is sort of, for us, the next generation computing methodology, problem, and everything. It encompasses all the learnings we've had from the 3 previous projects, and it allows us to have a single programming model that allows us to do both batch and streaming. In Google, we have 3 projects, essentially. But now with the data flow and Beam, we have 1 programming model. So how do you write a pipeline with the data flow, or Beam? So a Beam pipeline is directed a cyclic graph of data transformations. So B collections are, how many of you are Java programmers? Java, anyone? Okay, good. So you have collection, in Beam you have P collection, parallel collection, right? And you write transformations on these data collections, and that comes out as a graph. You can have multiple inputs, like here, we have 2 inputs to the pipelines. Okay. And you can have multiple outputs. You don't have to produce a single output, right? When you write your pipeline, you submit the pipeline to the system to execute, and system takes this pipeline, optimizes execution graph, and then executes the optimized graph, not the original one. So how do you write the pipeline? So there are a few pieces you have to think about. First one is the transformations you want to do to your data. The second one is how you are going to aggregate them. You can use this composite transformations to do really complex operations on the data. And you need to think about what your data is and how you encode it and decode it. It sounds more complicated than it is. So we'll take a look. So let's write a pipeline. So how many of you know about hashtag autocompletion? You know, you start typing and it completes. Familiar? Okay. So what does it take to write something that comes up with the model that allows us to autocomplete, right? I'm typing, in this case, Super Bowl, and I started Super BO, and I get all these suggestions for it. So how do I get the model for these suggestions? Well, I have a set of, my data model has a set of prefixes, and then the most popular words for this prefix, right? So we're going to compute this, given an input stream, like a Twitter stream, we'll compute prefix and the most popular words for that prefix. Okay, sounds okay? Okay, so how do we do it? Imagine I'm on the whiteboard. So I have my tweets, I'm going to read them, I'm going to extract the tags that I care about, I'm going to remove the go, the in English, right? I'm going to remove those unnecessary words. And then I'm going to count each of the relevant words. I'm going to count. And then I'm going to expand the prefixes. I need to get, like, for all the relevant words, what are the prefixes that they have. And then I'm going to select for each of the prefixes, I'm going to select 3. 3 that are most used, right? And then I'm going to write them, and then I'm going to go into the system. Okay? So this is what we're doing. Sounds good? Okay. So how does the code look like? Well, we have a pipeline. We begin the pipeline. We will read from the GS bucket, in this case. We'll apply extract tags. We will count each of the words. And then we'll expand the prefixes. We'll select top 3 for each of them. And we'll write our model to the output file. Okay. So this is the core of the pipeline. So a few concepts: the pipeline, the directed graph of steps operating in data. We had pipeline P, and we created it by calling pipeline.create. And then we run it at the end, P run. Our data is the collection, P collections, and they're immutable collections of the same type elements that can be encoded. And then you have more advanced collections, like collection tuples and lists. And so in this case, our collection is created when we read the text IO here. That creates a collection. And when we write, that created a materialized collection. And then transformations are all the operations we do on that data. Those are called the pardo's, parallel do, like do this in parallel. So this is extract tags, count, expand prefixes, top, right? Like all of these operations. And how do they look like? It's a regular Java code. You have interface you need to implement, but that's about it. We have expand prefixes. This is pretty basic Java code, but I think it does work. So we get the word. It's a key. From the key, and then for each of the letters in the word, we produce the output, the prefix and the whole element. We explode the data. It's good. If there is a bug, let me know afterwards. Okay, so this was the structure of our code. We wrote an application. Let's look a little bit more what the beam gives us, right? In addition to those steps that you can write, we have many transformations that we provide for your convenience. Things like lowercase, filtered out words, key by first letter, and things like that. We have lots of libraries that are already there, the transformations that are part of the SDK and library that you can use. What happens, so you've seen your pipeline, but what happens on your workers, right? When this runs on many different machines, maybe on 3, maybe on 3,000, right? So what happens on the individual worker? So imagine our input was ABC, D, and EFGH, right? When we partition the data, these are the bundles we ended up with. So what worker does, it calls this start bundle at the beginning when it starts processing this partition bundle. And then it calls process element A, that's the first one. Right? This guy. Then it calls process element B. Then it calls process element C, and then says I'm done, so I'm calling this finish bundle. Right? So this runs on the worker, and when the worker is, gets a new bundle, processes, gets a new bundle, processes until it's done. Right? It's in workers are this kind of a loop. Okay. One interesting, any questions so far? Everything is clear, great. So one interesting transformation that we have, and it's a core concept, it's called group by key. Right? In this operation, you take, you essentially take all the values that you, keys and value pairs that you have, and you produce the output where you group all the values that belong to the same key. So you can process it in a later step. This is a special kind of operation because it involves the usually expensive operation of shuffling, because your keys can be anywhere. This is sort of core of the MapReduce. If you remember my graph, like the triangles, all the triangles from all the data sets went to the same worker, right? So this usually involves shuffling between the workers, and it's common operations that people use. Okay? But one question you have to ask, we said that the beam is for both batch and streaming. So in batch, you know when you've seen all the keys, and you can do grouping. How do you know that when you have infinite data that's streaming? That's a tricky one, and we'll come back to that soon. Okay, so group by key, you can optimize with, often when you want to group by key, you want to apply something immediately after, and we call that combine, and then you can do some optimizations in addition to that, and then we come with the combine functions, because you end up doing, it allows you to filter data earlier, and this is a pretty popular thing, and improves the performance of your job. So we provide lots of combine functions that help. So if you wanted to compute the top n, in reality what top is, it's like group by key, count them, sort them, and then give me n, right? So you would write it like combine per key top fn, and you can shorten it. And we have actually a bunch of already created combine and functions that are part of the library. And some of the interesting ones I would like to call out are approximate quantiles. These are pretty complex to implement, and we already implemented them, and they're mathematically correct. So we have the beam itself is the SDK is very rich in these complex combined functions and group functions. So it makes it easier for you to get the end results you need. Okay, so let's go back to that infinite data where we want to do group by key. If we wanted to wait on all the data to see on infinite stream, you would never be able to do any grouping. So what do? We do windowing. And let's discuss what windowing is. So if you have an infinite stream of data, one thing you can do with it, you can do element-wise transformations, essentially something like a filter. So for every value you do something, you discard it or you change it or whatever. If you're doing just that, that's fine. You're just passing through the data through your system. But if you want to do any kind of aggregation, like group by key, find the maximum, find the minimum, give me the median, right? Like for infinite data set, you have to figure out like when to produce the result. And you do that like because you ask for the result in a given time range or in a given window. And the time range is just a common way to do it. So if you imagine the infinite stream from here, the x-axis here is the time when this data arrived to our system. So we could decide to produce, the top elements for the time windows between 1 and 12, 12 and 1, 1 and 3, 1 and 2, and etc. Right? This is you could do the group by key on this windows, hourly windows in this case. More interesting though is to do grouping and aggregates on the time when the event actually happened. So if you have your cell phone and you're playing the game, and you go into Subway or go into the garage and you lose the signal, but you're still playing the game, the data might not be sent to the servers, right? It can be sent with delay. If I'm the game developer or I'm the company that's doing this, I would want to understand what my user did, as opposed to what my user, like when I received the data from my user, right? So if we have this infinite data stream, and we can do the splitting according to the processing time, but more interesting and insightful information will be if you do it according to the time when the events happened. So in our infinite stream, that when it arrived, this green dot that you can clearly see, actually that arrived to us around 12:50, actually happened at 11. And this one here happened between 12 and 1. Right? So this one arrived in the same window. The processing time and event time overlapped, but this one was late because this one came almost at 1 p.m. but it was from 11. Okay, so these are two concepts: event time and the processing time. And more interesting is if you have users, you want to understand what are they doing, and a useful concept in that case are sessions, and this is something we use at Google a lot as a source of information for analysis. And the sessions are bursts of user activity. So if you imagine the stream of data coming, and you think that each red dot, like each color represents a single user. So these are all events from, I think 3 users, red, green, and yellow. So we can generate the sessions of their activity. Like, okay, so here they were doing like a lot of playing the game. Then they made a break, they played some more, then they played a little bit, then again a long session. It's like that, right? And this type of view on user activity, like in terms of these bursts, is really useful when you want to try to understand what they're doing. And this is the part, something that's a native concept in Dataflow. So the session windows and ability to generate this type of activity based on the event time is a native concept in Dataflow. Okay, so there are three types of windows that we do. One is fixed, like every hour, every 5 minutes, or something like that. Some are sliding. You can do sliding windows, so you have overlapping windows. Sliding, overlapping hourly windows. And then you can have sessions. And windowing enables aggregation by dividing the data into finite event time-based chunks. So now you have all the data that you need to group by key or you need to count. You have the whole data so you can emit the result. So another core concept when you have this event time and processing time is the watermarks. And watermarks track how does our processing time relate to the event time. So if you look at this graph, the events happen in event time. And this is the time when we become aware of them. If we were able to become, the process event the moment it happened, they will all land in this line, the dashed line. That's the ideal watermark. You rarely have ideal watermark. You usually have something that's somewhat delayed. There's a skew between my ideal and the actual watermark. And watermark describes the progress. It says like no timestamp earlier than the watermark will be seen. In other words, at this point, I don't think I'll see any events that are older than 2 p.m. Right? So there is a point in time and you think you're done with everything up to that point. Okay? So it's often is heuristic based. We can't get a perfect one usually. And that means that if it's too slow, the results come later. So if you want to be really conservative, you want to wait for all the data to come, then you cannot produce result until you have all the data. And if it's too fast, you'll have some data that is late. And we'll look at each of those. So when we emit the result, it's triggered by the, it's controlled by the triggers, and they're often relative to the watermark. So this is example, like we are doing the sum right now in this example, and we want to produce the result when we think we consumed all the data in that time window. So we're doing 2-minute windows, and we will trigger after watermark passes the end of the window. So we've seen all the data in that window, we produce the result. And we do the sum. Operation is the sum. So this is a very nice visualization of what happens in the system. But let me explain first what are you looking at. So here we have event time. Okay? Here we have processing time. 12:05 event time was here observed, right? Like, so the ideal watermark follows this line. And you can see all the events happened. We observed all the events after the ideal watermark, right? Our watermark, our system at this point thought that they saw everything. Like at 12:06, our system thought that they were done looking at the data from between 12 and 12:02. So the watermark progressed like this. This guy here is a late guy. So our result in this case is incorrect for this window because we didn't capture that 9. So we want to figure out what to do with that 9, and I'm going to show you what are the options. But any questions about this graph? Because the next graph is going to get even more complicated. Any questions? You want to know how it's made? The graph? It's a lot big. Okay. So let's see. What do we do with the late data? Oh, yeah, there's one more thing. So until this watermark passed, we couldn't produce any output from this window. You know, maybe you want that, but if you're making a dashboard or something that someone is monitoring, you don't want to wait for a long time. I mean, these are 2-minute windows, you can wait. But if you had an hourly window, you really want to see what's going on in this hour. You know, even though it's speculative. It's not the final data, but you want to see what's going on. So, and at the same time, we want to address the late data. So this is how we do it. So this is the original code. We had fixed windows. We had the trigger at the watermark, and we did the sum. So now we still have fixed windows. We still do the triggering at the same time. We still do the sum, but we do the following. We want to produce early results after we've seen the first element and every 1 minute after that. So we produce the early result a minute into the window after we saw the first element, okay? And then for the late data, we want to produce the new result every time we see a late data, okay? And we will allow lateness of 1 day. So if you're more than 1 day late, you'll be dropped. Okay? So how does the graph look like at that point? So here, the 5 came out as 5, but now we were able to pick up value for 9, and we had the correct result there. The second window is interesting, because we got the result for 7 within the first minute of that window. That's because we had that speculative data set up, right? So it produced the speculative result after 1 minute, then it produced another tentative result, speculative result after another minute, so that's the 14. And then it produced the final result when it finished, when the watermark crossed. Okay? And similarly for this final window here. So this is pretty complex logic. In Dataflow, it was equal to configuring the windowing behavior and triggering behavior that we want In another programming models like Spark, you would have to implement this windowing logic yourself. And I think equivalent is like something like a few hundred lines of code. And good luck debugging that. This one we debugged. Okay, so this is one of the things we do. We have actually more advanced triggers, even more advanced than this. We have a session windows and session triggers, and they allow you to see your data in a different view than just like this time-based splits. But I think we'll talk for quite a bit. So let me step back and talk a little bit about Apache Beam, technical vision. Okay. So the Apache Beam hopes to serve the three groups of people. The first one are end users, engineers who want to write the pipelines, who need to compute the data, right? We clearly want to support them. And for them, we build a Beam Java, and we're working on Beam Python, and we have other languages contributed, and discussed about Beam Main. We also want to support the SDK writers, the people who write these languages. Like, for example, we have Scala data flow contributed by Spotify. So Spotify wrote the Scala Beam SDK. And essentially, we want to support SDK writers who want to do that too, because they enable Beam to be accessible to folks who don't program maybe in Java or Python. And then we have the final group, the runners. And the cloud data flow is one of the runners. But we have Flink and Spark, and we want to be able to grow that community as needed, right? And to achieve that, we structured our code in the following way. You have SDK, and all the SDKs produce the same pipeline construction model. Like, you can code in whatever you want, but you produce your pipelines are described in the same way. So any of the runners can pick them up and run them. So we provide this, this gray part is the standardized thing that the Beam defines Beam model. And then in the runner, like each of the runners translate into whatever they need, but then we again have a standardization point that allows it to be executed on many other, on other runners. Okay, so this is the last slide from the writing the Beam pipelines. Any question about what you've seen so far? Okay. So this type of slides is available on beam.apache.org. So we have some community slides available there. We also have two excellent posts about the streaming. It's called Streaming 101 with O'Reilly. They're available online if you just do Streaming 101 and throw in the data flow word or Beam in it. There are two posts by one of my colleagues that explain in detail the model and the philosophy and why it's important to, and why we have done it this way. They're excellent reading posts for the background. So, and Google search will give them to you. So, again, the same person did this graphs, and they're pretty cool. Okay, how much time? Okay, so we're, again, you've heard about the data flow. It's the best place to run the Beam. It's fully managed. It's integrated for our cloud logging, cloud debugger, cloud profiler, and there is no tuning required. When you run a Beam pipeline, it looks something like this. You get the UI that shows you your graph. This one, I just scraped this off like from one of our test jobs. But you know, essentially, you can visualize your pipeline, and this guy had the two outputs, and from a single input. And you can track it, you can see your logs and everything else through this UI. We have some advanced auto-tuning techniques that we have, and we also have some good blog posts about them. Again, this is the auto-scaling in action for streaming and auto-scaling in action for batch. Apurva talked about that. And here's the final slide with the links to more resources. we gave a pretty detailed talk on at scale 2015. There's a YouTube video of that talk. So if you try data flow at scale 2015, YouTube will find you the right link. There is a data flow model paper, which is an academic paper that came out on BLDB last year. And this is the website for Beam, and this is the website for data flow and the Google Cloud Platform. So show the stack again. Beam, data flow. Any questions? Okay. No, thank you for your time.
Do you want me to do the demo, or are we pretty much done?
Right. You were going to do like data talk.
Data prop demo. Yeah.
Yeah.
各位，我们今天这一场如果没有听得很清楚，我们 YouTube 是有 record 的，你们到时候可以跟我拿那个 URL，你们回去可以再看一下。大概2个 session 我都有把它录下来。
Alright, so I'll do a quick demo of data prop. I know most of you are not Hadoop Spark users, but at least wanted to come to see. Won't take more than 5 minutes. I know it's getting late. So if you are familiar with Hadoop Spark, or even if you're not, one of the fundamental premises here is that you can create a cluster of a few nodes. And let me demonstrate how easy it is to create a cluster. Let's name it.
Yes.
Whatever. I think this is something for so now you can identify the zone in which you want to create this cluster. These are all the different zones where GCP has capacity to create a cluster. I'll pick some random zone here. All different type of machines that you can pick and choose from. So you can go from a machine with very bare bones, one CPU, one virtual CPU machine, to a machine that has 32 virtual CPU and 208 gigs of memory. So you can choose what you actually want. Let's just stick with a standard machine so that you can identify, or you can actually allocate the disk of your choice, 500 GB, a few terabytes, whatever you desire, and you can actually pretty much hit create, and the job will be pretty much done for you. So the cluster will be done. You can actually, remember I mentioned preemptible VMs. You can even identify a couple of preemptible VMs. Let's just put that. Obviously, if it's a preemptible VM, you cannot have storage with it, because the whole notion is it's going to disappear. So let's hit create, and hopefully this will work. So you can actually start seeing the cluster is being provisioned as we speak. And as the cluster is being provisioned, you should be able to see some information on this cluster. Now, what are the VM instances? Remember, every cluster has to have a master node. But along with that, we provision 2 workers. And we provision 2 preemptible workers. So in about maybe 90 seconds to a minute, this worker is already provisioned, as you can see. The entire cluster is provisioned. We go back, and the cluster should be up and ready for us to use. So we go back and see if I can cover this. So the cluster is in the final stages. You can even click on the instance itself, and it'll give you, all of the details of where the information is going to be stored, where some of your buckets are created, the location. You can dig through a lot of this information as well. Go back. One other thing, while the cluster is also being created, I can submit a job, very easy enough job to this cluster, and I can pick and choose. Even though the cluster is not quite ready, I can submit a job right now, and when the cluster comes up, I should be able to run it. I have different type of jobs I can submit, from Hadoop, Spark, PySpark, Hive, Big, anything of my kind. I enter the jar file name, my actual class I want to run, my actual jar that I'm executable that I want to run. I can specify a bunch of arguments to that, and I hit submit, and then I can run. It's as simple as that. So again, remember, there's not much you have to do. On top of that, I want to show one other thing. It's an interesting, you can do exactly the same stuff as a part of command line process. Let me initialize this. gcpug is one of our SDKs. Initialize it. I'm just going to reinitialize this. I'm going to use my login because I'm the one running this. And let's go back and let me show you. The project I'm using is Hadoop demo up here. So I'll pick and choose the same project so you'll actually see. It is number 39. So let's pick 39. And let's pick the same zone. We picked, I think we picked them. Let's pick a zone, doesn't matter which zone. So at this point, I should be able to create a cluster, and I'll basically, along the way, I'll have a lot of information that I need. I'm not sure exactly what this is. I have an option to do data prompt, which is what the project is. So let's do gcloud data prompt. Let's see what options we have as a part of data prompt. I can create clusters, I can submit jobs, I can do some operations on it. So let's do clusters. See what options this is going to provide. I can create, I can delete, I can describe. Obviously, let's go ahead and create it. So, and remember all of the options you had: machine type, how many nodes, where do you want to create it, what is the name of the cluster. Everything is available in command. So I can specify that, but in the interest of time and keeping it simple, let's say, what did we call the first one? Type A, type 2. And that's it. This is going to create a cluster with all the default configurations. So let's go back and take a look at a cluster. It should be up and ready. Type A, my tech is up and ready. Type A, my tech 2 is coming up. So very, very simple, extremely easy to use. As I mentioned, the clusters come up really fast. Unlike any other system out there that will take minutes, sometimes even hours, depending on the size of the cluster. It is blazing fast. And this is what supports your ability to spin a cluster, run your job, destroy. Again, unlike any other system that's out there. And that's actually pretty much everything I wanted to show in this quick demo. Any questions on this? Anything that I can answer? And just for the grins, the cluster is still being created here. About by the time we wrap up, cluster will be up and running.
You have demo for Data Lab?
I don't have any demo for Data Lab just yet. It's in alpha or beta? I keep forgetting.
Yeah, they're like an alpha, I think.
It's still in alpha. So once we have a beta part, I think we'll give you a quick demo. Right now it's opt-in. Essentially, you have to invite us. And by the way, the cluster is up and ready, so hopefully this will show up as my demo. So as we were talking, the cluster basically came. So very, very quick, very easy. All right, cool. Thanks, guys, for listening to me. If you have any questions, we'll hang out for a few minutes. It's been a long 2 weeks for me, so if you don't get coherent answers from me, apologize. I've been in Tokyo, I've been in Seoul, I've been in Mumbai, I've been in Delhi. This is my last destination before I head back. So, thanks, guys.
Just to say, like this stream 101 and the slides that she was talking about, I posted that to the Facebook event. So the event on Facebook. Yeah, well, the gcpug Google user group event. I also posted the group, but the admin has to like approve it, so someone doesn't have it. Yeah, so you should be able to find it later. Yeah, no problem.
Kai-Chu秀，Kai-Chu秀。